Okay, thank you so much, Corrie. Can you hear me? Is this on? Hopefully you can hear me, yes. Thank you so much, Corrie and James and the entire Innovation Oz team, not just for this event, but also for the work that the team does, Innovation Oz does every day in highlighting the significance of research, science, innovation and manufacturing to Australia's future. Even in the bleakest of times, Innovation Oz appears on our screens every second day or every third day with interesting information and analysis of how we are placed in the world and how far we still have to go. So it's very exciting to be here in Canberra, talking about science, technology and innovation, and indeed with a government now in office that actually believes in climate change, wants to do something about it, doesn't hate universities, wants to make a difference for all Australians, including First Nations peoples. And it isn't just about government, it's about all of us making a difference because we have the opportunity to do this with the government putting wind in our sails. And it's a government and something that we all know that research and innovation is absolutely central to our future. Of course, we can't do everything. We only do 2% of the world's R&D. We're not going to be excellent at everything. But when we look around the world and see the scale of ambition of other countries, the question we ask government now is not, is this too ambitious, but is it ambitious enough? If we just think over the last few days about the Biden industrial policy legislation, 280 billion American dollars, 400 billion Australian dollars, eye-watering amounts of money going into the research, innovation and manufacturing system. If we think of Australia being 10 times smaller than the US, that would imply we should be spending another $40 billion on research and innovation. But we spend only about $12 billion a year as it is. To add another 40 billion might be a little bit ambitious, but that's where other countries are at. We're about 1.79% R&D as part of our GDP. Other countries are pushing at 4 and 5%. So we have an enormous way to go. But even though we only do 2% of the world's research and innovation, we are still very good at what we do. And no one more so than the person sitting to my left, Michelle Simmons, who is leading the charge on quantum computing, a new area of technological innovation for Australia and the world through her Quantum Computing organisation, but also as part of a growing ecosystem, especially in Sydney, but also other parts of Australia, but in Sydney around the newly formed Quantum Academy, which is part of Tech Central in Sydney. So my role here is to ask Michelle some key questions about quantum. It won't be everything you wanted to know about quantum, we don't have the time, but we'll certainly, I think, nail a few ideas that which are going to be essentially game-changing, changing the world in the future. And I'd like to begin by asking Michelle, and I won't introduce Michelle and all her affiliations, that's all in the Innovation Oz newspaper that we have in front of us, but I want to start by asking Michelle about her latest breakthrough, which is manufacturing integrated circuits at atomic scale and what that means for the quantum computing endeavour. And I do want to emphasise that, like most of you, I love quantum computing, but I'd really like to know what it's about. Over to you, Michelle.
Thank you, Roy. Look, I'll start with that breakthrough because it really is something that I think is pivotal for Australia and obviously for our team. But essentially what we've done is made an integrated circuit that's done a calculation where the fundamental units are atoms. And to put that in context, it's really worth looking at the classical computing field and seeing what happened way back at the beginning before computers are around everywhere as today. And so we go back 1947. In 1947, at that time, computers were made with kind of vacuum valves. They were very unstable. There were many thousands of them. They're about the size of my hand. And they were not very reliable. And so in the US, a group of engineers and physicists said, well, actually, we can get rid of these vacuum valves and we can make digital information in semiconductors. They used germanium, a material at the time. And they showed that they could switch between ones and zeros, on and off states for digital information in a small piece of semiconductor. So that was the first transistor in 1947. And then they realized very quickly, if we want to make a computer, we've got to figure out how to put lots of these together. And so they figured they could actually do it by integrating it all on the same piece of germanium. So in 1958, they got 8 components on germanium that all worked together. That was the world's first integrated circuit. Now, both of those won a Nobel Prize by different groups, but it really was the beginning of the computing era. It was another 5 or 6 years before they actually used it in any kind of product. And at that time, it was used for hearing aids and in calculators. And then it took till 1971 before they actually made the world's first industrial computer. So now we look at quantum computing. Quantum computing has a similar kind of trajectory. And so we can use that as a roadmap for us to know how long it's going to take to build a quantum computer and what are some of the challenges we need to do. In the quantum computing world, to access quantum states, we have to make things very small, so down at the level of individual atoms. And that really was the challenge the Australian team set itself back in 2000. So in 2012, we made the world's first single atom transistor. So a transistor that used literally one atom, one electron to switch between on and off states. Our goal was then to try and replicate the 11 years to get towards the integrated circuit, but now at the atomic scale, which would have put us in 2023. We actually got the result at the end of 2021. So we made the world's first integrated circuit with atoms 2 years ahead of our original schedule. So that's very exciting. Thank you. And it's exciting for a couple of reasons. First is that it's keeping us on that roadmap to building a large-scale, fully programmable quantum computer. But the second one was we wanted to see if we could demonstrate something. And that's the second part that probably is the bit that we're most excited about. Not just a technological demonstration. We went back to what Richard Feynman said, and he said back in the 1950s, if you want to understand how nature works, you have to be able to build it at the same scale that nature operates. So you've got to be able to build things at the atomic scale. So what we did with this device was we actually simulated an organic molecule called polyacetylene, and we showed that we could literally, with sub-nanometer precision, mimic the actual single and double carbon bonds of the polyacetylene molecule. One of the things we had to decide was if we make this molecule, we've got to make it small enough that we can use classical computers to predict how electrons would flow through that molecule. So we chose literally a 10-dot system, a 10-carbon chain, and then we basically mimicked it. And because we knew theoretically what the classical computer could predict, we made 2 devices, we chopped it between a double bond and chopped it between a single bond, and we got completely different signatures that had been predicted classically. So that really tells us that we can mimic nature for the first time using our technology. And the exciting thing about that is, A, it tells us what we're going to do next, but B, if we now just go to 20 dots, we're beyond what classical computers can predict. So we're falling off the edge of what is classically known into that quantum world. So it's hugely exciting for us.
Thank you, Michelle. So can I ask as well, what are the steps beyond this breakthrough to developing a fully fledged, as you say, fully programmable quantum computer? Because we're not there yet. There's still a lot to do. And it's also not just going to happen here. There's a number of mammoth research projects around the world. Where will it happen and how will it happen, do you think?
Yeah, look, so the next stage, there's lots of technical milestones to the next stage. We want to make our first product. We predict we'll do that in the next 5 to 6 years. We're very excited about that. But then we have to bring in something called error correction, and we call it building up the stack. We have to integrate fast control of the qubits, software layers, and it's literally the whole computing industry redone again. And what's fabulous is Australia has incredible depth in all of those areas. So we actually realised that we can actually do a lot of it onshore. So we can actually build the whole system here in Australia and manufacture it in Australia to be accessed globally. So that's very exciting. But obviously it's a global field, there's a competitive race. Australia sits incredibly strongly at the forefront of that race in so many areas.
And so imagine 5, 6, 10 years' time, we have a quantum computer in front of us, what will it do? How will it change the way we live and work?
Yeah, look, there's so many different areas now where quantum computer comes in. With the simulator, the device I've talked about before, we can start to look at new materials that we don't understand. So one of those is high temperature superconductivity. We don't know how it's formed, but we can actually start to mimic that in our labs and then see how to make it work. Looking at catalysts, so it's kind of well known that nitrogen is a fertilizer for the agriculture industry, but it relies on a nitrogen triple bond, which is very strong. To break that actually takes a huge amount of energy, huge cost, and it actually produces 2 to 3% of the world's CO2 production just for that process alone to create fertilizer for the food industry, for the agriculture industry. So if we can figure out how to make a more efficient catalyst by mimicking it with this kind of systems, then we'll be able to have a massive impact on the agriculture industry. But then it goes beyond that, the transport industry. Anything where there is a large and complex problem is where quantum computing will start to make it accessible. And it hits pretty much every industry vertical. Drug design, transportation, logistics, banking. It literally is amazing. So it's a transformational technology that will be both strategic and economically important for Australia.
So quantum computing has been singled out as an area of potential competitive advantage now for Australia. And I wonder, how can we apply this across the research and innovation system more generally? If we can take a step back and ask you, given your experience and your observations over the last few years, what do you think works best when we're developing a coherent, much more effective, we hope, research and innovation system across Australia? How should we structure it? What is the scope for competition? What is the scope for cooperation and collaboration? What are the kind of institutions we need? Quite apart from the amount of resources we devote to this, what are the structures you think that work best?
Yeah, look, I think one of the things that we've kind of trialled in the company is really bringing together government, industry and university together. I think that's something that is incredibly powerful. I think one of the things Australia tends to do is underplay where its strengths are. And certainly we've had a fantastic research system with the Australian Research Council with centres of excellence and research fellowships that have brought people from overseas to work here and expand and take on these ambitious projects. And of course, one of the challenges now is how do we get all that world-leading research, how do we get it out to products that benefit Australia and build the economy here? And I think for us what we've realised is we're in a unique position globally where we can bring those three sectors together to support our researchers to translate. I know for sure that when we did that back in 2017, we actually had a lot of people from overseas saying, gosh, we wish we could do that here. We actually hired one of the lead hardware engineers from Google, who got the quantum supremacy result. He came over here and he said, I wish I could have done that with Google in the US. I wish I could have got government behind us. So having those three sectors working together and breaking down the silos between them, getting behind universities, making sure that we get industry directly involved, I think that's been fantastic for us. That really has allowed us to get to this latest breakthrough, and it's allowed us to see the way forwards.
Since you raised the question of Google, many of us have seen over the last week or so, wasn't exactly a controversy, but certainly an intervention by the new Industry and Science Minister, Ed Husic, about the danger of intellectual property that we develop in Australia being commercialised overseas. And given that Google had just reached an arrangement with a number of universities about the development of quantum and the prospect that this might have of doing what happened, as we've seen in the past, with photovoltaic cells, with wireless LAN, so many things that were invented here and then commercialised elsewhere. Minister Husic quite rightly raised the big flag around this issue, but at the same time the universities and Google seem to have contracts in place that would retain the intellectual property in Australia. How do you approach this issue, and how do you think we should safeguard what we're doing, while of course sharing knowledge with the rest of the world?
Yeah, look, it's a great question. I think one of the things that we realised when we set up the company was we wanted to control as much as the manufacturing and the process here in Australia, because fundamentally when you're developing hardware, you need to have the full supply chain here so you can actually manufacture in-house. That makes you go fast, and it gets you a product much sooner. And so we've really focused on that, recognising that it is a global world, and we're going to be collaborating, we're going to be selling overseas in the long term. But I think, I really take to heart some of the things that the Minister said. His latest mantra is more onshore. I absolutely believe in that, because in any country you want to make sure that you have that high technology growth from within. And obviously not everyone can manufacture their own products here, so would have to get things from overseas, in which case you do need to partner. But I think it's absolutely critical that we support those Australian companies where they're building and manufacturing and testing here, because fundamentally that's where the big changes, the transformational changes and the economic returns will come in the long term.
And of course what you're doing with quantum is in fact part of a return or a reinvention of manufacturing. How do you see the future of manufacturing in Australia? I think many people here are interested in understanding what future we do have, given that manufacturing is now only 6% of GDP. It was around 25-30% in the 60s, went down to 12%. Then we had the commodity boom, windfall gains that we didn't reinvest in a way that would have prepared us for the future. And now, as the Productivity Commission pointed out the other day, we have historically low productivity. We know we have wage stagnation. We have huge challenges around climate transition, and all issues around productivity concerning the distribution of income as well. So these are huge challenges. What role do you think manufacturing plays in achieving a more complex and diverse economy and preparing us for the future?
Look, I actually think it's critical, and it's our responsibility to do it. So fundamentally, obviously, manufacturing, if it's mass manufacturing and cheap, that's something that's going to be very difficult to Australia to compete with. But if you go for the high-end manufacturing, if you make goods that, like a Swiss watch, precise, high-end, high-value, transformational areas where Australia leads globally, I think that's where we should get in. We've got a fantastic research workforce, highly trained. Our young people are hungry for this. So I absolutely know a lot of them want to get into setting up companies. They want to build things here. So it's really our responsibility to create that opportunity for them. And people come from all over the world to work and live here, because it's such a fantastic place with a great, research sector. So we shouldn't underplay it.
So just one more question, because I think we have to move on at this point. It's often commented that the culture in Australia is not conducive to innovation, and you're giving very powerful counter-examples to that we are a very ingenious country. We can do it if the structures around us are right. But it's often said, especially given the fact that we, on all the international indicators, lag in our collaborative arrangements between research and industry. Are the incentives right there? Can we improve the incentives towards collaboration? As we know, for academics, a lot of the incentives are around publication in top-tier journals, not necessarily to engage with industry. And on industry's side, there's a lot of barriers that they see in connecting with universities. Yeah. In the UK, for example, there are the Catapult Centres. In Germany, Fraunhofer's. In America, there are a whole range of institutions. What kind of institutions or incentives do you think we should develop here? And what sort of advice, in other words, would you give to Minister Husic over the next few years to bring about that more collaborative culture?
Yeah, look, I think it's a very difficult question, but yeah, I've read your papers as well. So I think, fundamentally we've got to invest more funds into our translation. You can plot the technology readiness level from the basic research all the way through, and I think it's good for us to look at all of those in the way that you've suggested and rationalise where we put funding. But then we've really got to get behind, particularly in the physical devices space. There's been a lot of funding going to medical research in the physical devices space, where Australia absolutely leads. So many Australian quantum companies are world leading, sitting right here, and they need that boost. And bringing industry, university, government together to help them across, it can only be beneficial for the whole country, to be honest.
Thank you, Michelle, for being with us today, and also we look forward with great anticipation and admiration to your future work.
Thank you
so much.
Lovely talking to you. Thank you.